All engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello and welcome to the programme where we bring you the latest breakthroughs in science, technology and medicine. I'm Chris Smith, and in this week's programme, it's Q&A time. Coming up, we'll find out what can we learn from invisible measurements out in space, how do scientists discover potential new medicines made by plants, and why might green energy be more costly to the consumer? Yep, we're answering the science questions you have been sending in.
The Naked Scientists podcast is powered by ukfast.co.uk.
Now, in a moment, we're kicking off with why carbon dioxide turns out to be so critical for our food supply, particularly here in the UK at the moment. But first, let's meet the team who are here to be your living and breathing Google search engines. Atmospheric climate scientist Ella Gilberts from the University of Reading. Now, you study one of the Antarctic ice shelves. I didn't know there was more than one.
They fringe the Antarctic continent. They're these kind of floating platforms of ice that form when the ice that flows off the continent hits the ocean and spreads out.
How big are they?
They vary in size. The one I particularly focus on is called Larsen C. Until quite recently, it was the fourth largest ice shelf on the continent. I'm going to fudge that because I don't know the actual size of it anymore, because it slipped down the rankings to number 5 after losing a gigantic chunk in 2017. So they are rather large.
Well, there you go. Anything Antarctic, that's going Ella's way. Also with us is Gernot Wagner, who's a climate economist. He's at NYU. He's also author of a new book called Geoengineering: The Gamble. Well, what is geoengineering and why is it a gamble?
So it's lots of things to different people. On the one hand, it's sucking CO2 out of thin air capture. On the other, and more controversial, it is basically mimicking volcanoes, trying to make the planet more reflective, shooting stuff into the stratosphere, cooling the planet underneath.
What the idea being that because we've warmed things up too much, if you make the atmosphere more reflective, then less heat comes in, and that helps to cool things down.
Exactly. And, the idea is simple, right? It's the reason why we wear black jackets in the winter and white shirts in the summer. Lighter colors reflect more light, heat, energy, and cool what is underneath. But it's a gamble. It's quite a big one.
And perhaps we'll find out a bit more later on in the programme about why. Also with us is Emory University ethnobotanist and also herbarium curator. That's Cassandra Quave. She is an intrepid explorer. She looks at how we interact with the plants around us around the world, including how some of them might be able to supply us with some powerful new medicines. And she's written a new book that's called The Plant Hunter. You must have had some interesting times then, looking for exciting plants in exciting places.
Oh, absolutely. I love to travel and I love meeting new people and speaking different languages. So ethnobotany is the field to be in if you enjoy those things.
Why is it called ethnobotany? What's actually the root of that word, if you excuse the pun?
Yeah, ethnobotany is the scientific study of the relationships that people have with plants. So it might be the way that people use plants for food or medicine or clothing. And as a medical ethnobotanist, I'm really interested in the medical applications.
Looking forward to hearing about that one. Also with us, Matt Bothwell. He's Cambridge University's public astronomer. Every time, Matt, I hear that term, public astronomer, I think back to this guy called Robert Simmer, who was a barefoot philosopher because he used to keep taking his socks off in public to rub them on things and make static electricity. I presume you don't rub stuff on your telescope, but is this a new thing for you to be out there telling people about space?
I've been doing it for a few years. I was a postdoc for around 10 years or something, studying some of the most distant galaxies in the universe. But then over time, I think I realized I like talking about astronomy and sharing my excitement about astronomy more than I liked actually sitting on top of mountains and doing the observing. So I've left for greener pastures.
But you had your pen out because you've been writing books as well.
That's absolutely right. I've written a book called The Invisible Universe, which is a guide to all the cool stuff in space that we can't see with our eyes.
And perhaps you can tell us a bit more about the cool stuff in space that we can't see with our eyes later on in the programme. Now, if you're familiar with these Q&A shows that we do, you'll know that there's always a Guess Who quiz that runs through the programme. We give you a series of clues and that helps you to identify the mystery thing. And perhaps you'll see if you can get to the diagnosis of the mystery thing faster than our panel can. First clue coming up. So we're asking who or what made that sound? Ella, any idea?
Sounded like Daffy Duck to me.
Daffy Duck is not a cartoon character, but it is an animal. Okay, so I suppose you're sort of on the right lines, but don't worry if you need a few more clues. We'll give you a few more tips later on in the programme. Now, Ella, this week you've probably been watching the headlines here in the UK. Food production is apparently under pressure because of a lack of CO2. Listen to this.
The threat comes after 2 huge fertilisation plants in Teesside shut down due to gas price rises. CO2 is a byproduct of fertilisation, and the supply constraints could be felt across the food and drink industry.
So on that subject, Cornelia's wondering, Ella, why the shortage of CO2 should be causing problems in the food supply chain. And at the same time, we're continuously being told there's too much CO2 in the atmosphere. We've got too much of the stuff. What's going on?
I know it's a bit of a head scratcher, isn't it, that you can simultaneously have too much CO2 and too little. So I guess the thing to say first off is that CO2 emissions or carbon dioxide emissions are the primary cause of climate change. CO2 is a greenhouse gas which forms the atmosphere, which makes it a problem, of course, which is why we're constantly being told that we need to reduce our CO2 emissions so that we can have less of an impact on the environment, less of a climate impact. But when we're thinking about the food industry, it has a variety of different uses. So things like carbonating drinks. And as I only learned this week, for killing pigs, apparently, these sorts of uses require a lot of CO2 and you have to manufacture it. Lots of those plants manufacture it as a byproduct of other processes. So things like fertilizer, I think. In the atmosphere, CO2 in relatively low concentration. So at the moment, we've got 420 parts of CO2 for every million parts of air. So it means that to actually concentrate that CO2 into a thing where you could then inject it into drinks, it would actually be very, very challenging because we don't have the sorts of geoengineering techniques that I'm sure Gannett will be talking about later, like carbon capture, to actually sort of distill them into a really concentrated forms.
Indeed, because one big source is methane, natural gas, isn't it? That we then rip away the hydrogen off of it and turn the carbon that's in it into carbon dioxide. That seems something of a contradiction when we're thinking, well, we're trying to get rid of CO2. Why can't we use the stuff we've got in the atmosphere? We're told that we've increased the amount of CO2 in the atmosphere by enormous amounts since the Industrial Revolution. So if there's so much there, why is it so difficult to just grab it back?
As we speak, the very first demonstration plant like this is in fact operating. So it's a Swiss startup, Swiss company operating in Iceland, taking CO2 out of thin air and concentrating it. Now, it costs them about 1,000 euros per ton of CO2, which is incredibly costly if you look at it from sort of lots of different perspectives. And frankly, it doesn't pay to do that for food. It is too costly. But of course, costs are only going to come down. And, you need to start at 1,000 to get to 100 eventually and so on. So yeah, the technology does exist. It's just very pricey.
How does it work?
In some sense, in a sort of chemical sense, it's literally reversing the process that we use when we burn fossil fuels and release the CO2 into the air, right? So, that alone sounds energetically very costly. There is a reason why the Swiss startup is operating in Iceland. Why? Because there's a lot of cheap geothermal energy, cheap and low carbon, zero carbon. Those are the key ingredients here in this process.
Is that the way it's going to go then? Do you think that what we'll end up doing is we'll put CO2 scavenging plants where we're currently seeing a waste of energy, things like hot rocks, volcanoes, so there'll be certain countries where their growth industry in the future could actually be pulling CO2 out of the atmosphere and then turning it into stuff?
Here's hoping. Way too many people who make too much money taking fossil fuels out of the ground, burning them. And of course, to be clear, right, this process itself is useful, right? It provides energy. But, by now we have better ways of doing that, cheaper ways of doing that. Solar photovoltaic, solar PV is the cheapest form of electricity in history as of now. So there are better ways of doing that. And yeah, we should stop burning fossil fuels. And yes, there is already too much CO2 in the atmosphere. We should, and frankly, will be taking that CO2 out at some point at a cost.
Cassandra, you go all over the place hunting for plants that have exciting medical properties. Presumably, one place you can start is to ask the locals.
Yeah, absolutely. That's one of the main ways that ethnobotanists learn about the uses of plants is through interviewing locals or also looking at historic literature. We've looked at records going back to the 1600s of plant uses in different parts of the world.
Because one thing that's got me concerned is that you're doing this work, but the plants that those locals may know about may, thanks to the effects of climate change, not be there for much longer.
Absolutely. I mean, we're facing a crisis on a global scale when it comes to the impact of climate change on the availability of many of these plants. I can give you some statistics on this. We know that there are around 374,000 species of plants on Earth, and roughly 9% of those are actually used as medicines by people. When we think about plant-based medicines in the West, we often think of, herbal teas or dietary supplements or these kind of commercialized versions of these. But actually, billions of people across the globe rely on plants as their primary form of medicine, and they're acquiring them through harvesting them in the wild during peak seasons of when they're in flower or fruit, and then storing them throughout the year in their home or growing them in their gardens. And for those wild harvested plants, there are challenges that are arising as we see ecosystems impacted. When you think about the optimal climatic zone, the optimal elevation point at which different plants grow, after a while, as climate change and environmental factors encroach, you start to run out of mountain as the plants migrate up. And so, yeah, there are some serious problems with supply.
Somewhere, I think I read that about a third of the drugs that are at the top 10 list of things that are in your average doctor's bag or your average hospital formulary have their direct roots in nature and in plants.
Yeah, absolutely. The World Health Organization has a list that they come out with. It's called the World Health List of Essential Medicines. And if you go through that list, you can see many, many examples of drugs that we use today to treat cancer, heart disease, pain, malaria, infection, all types of different diseases. And the chemicals that are used in those drugs and the structural blueprints for many of those cases were originally derived from plants.
Why do plants need an anti-malarial, though? Just to take an obtuse example, what's it doing in the plant? Is it just luck that the same molecule, when you put it into us, helps to treat malaria, and in plants it does something different? Or are there some shared characteristics there? Plants make these things to ward off the same sorts of problems that we get.
First, we have to set this idea that plants are really some of the best chemists that exist on Earth. They have this amazing slew of compounds they produce. So even in a single leaf tissue, you may have hundreds of distinct molecules. And some of those molecules are useful for processes of photosynthesis and just simple growth and reproduction. But many of them are what we call secondary metabolites. And these are the compounds that plants use to defend themselves from pests and from herbivores that get a bit too greedy as they munch on their leaves.
Otherwise known as
Or,
vegetarians, is that what you mean?
yeah. So any kind of animal that gets to get a bit too munchy on a plant, plants can actually change their metabolism. They can actually upregulate and start to produce higher levels of poisonous compounds in their leaves to deter or repel other organisms that are harming them. And in the same sense, they can release compounds that attract pollinators and seed dispersers. I like to use the example of the corpse plant. I don't know if the audience is familiar with that, but this is sometimes in botanical gardens, and they call it, Mr. Stinky. It's the Titan arum. And when it blooms, it has this amazing smell of like a rotting corpse.
I
Poses
like Ella's
questions-
face when you just said that, which said it
It's
all
like,
pretty
imagine-
much. But no, they did have one of those at Cambridge University. They don't flower very often, though, do they? It took decades before this one was big enough to flower, but apparently the smell was really something to write home about.
Exactly. They're found in the wild in Indonesia, and I came across one not in flowering state, but in its leaf form once in the forest. It was just amazing to see it. I felt like I was a fangirl by seeing this plant. But it poses this question of, why does a rose smell like a lovely rose, and this Titan arum smell like a rotting dead body? It all comes down to those chemical signals. They have different pollinators and different organisms they need to come to them, because plants are sessile. They can't get up and move away from threats or go towards resources that they need. So they rely on these chemical signals to really recruit or repel other players in the ecosystem.
Amazing stuff. Cassandra, thanks very much.
From baffling British weather
Sideways spines of the vertebrae coming off here.
to looking at a cheetah from the inside out, games making their way to the clinic, and what to eat in your garden. The Naked Scientists In Short podcasts bring you a top-up of short, compelling science stories. Listen and download for free at nakedscientist.com/short or subscribe to Naked Specials wherever you get your podcasts.
Still to come on this week's Q&A, plants that can fight antibiotic-resistant diseases, and our Naked Scientist quiz, can you beat our big-brained panel? Before that, though, time for a bit more on our Guess Who quiz. Here's your next clue. Earlier on, I told you these things sound like this. And Ella correctly speculated they are alive, they're an animal. Here's your second clue. These are mammals, so you're right, Ella, and they're indigenous to the Americas, Eurasia, and Africa. That really narrows it down on the animal front, doesn't it, Gernot? Any thoughts?
No, I don't. I don't know what we could be looking at here. You need to ask my 10-year-old about this one.
A 10-year-old might be a good person to ask. We'll see. More clues coming up later in the programme. Well, let's head up into space now, and that means this is coming your way, Matt, just to forewarn you. In the last few days, NASA have announced the landing site for another rover. This one's going to be called Viper, interestingly, and it's heading to one of the coldest places in our solar system, which is, Matt, you can tell us?
The Dark Side of the Moon.
There you go. Not just a Pink Floyd album. It is the South Pole of the Moon. That's where they're going. And it's planned for 2023. Not NASA's only foray to our nearest neighbour out in space, though, because there's the intention to land another crew member on the surface of the Moon in 2024. And this has got Joel thinking. He says there's been a lot of discussion concerning a return to the Moon. So why are we going back? Why can't we just send a rover for that? Why send a human?
It's a really good question. And I think there's a short-term answer and a long-term answer you can give. In the short term, it's useful to send people rather than robots to the moon because there's only so much you can do remotely. Human beings are really good at being adaptable and flexible and responding to things in the moment. So, if you notice something interesting looking on the horizon, or maybe you have some lunar dust on your experiment you want to clear out, sorting that stuff out is trivial for humans, right? You can just wipe the dust off your experiment. If a robot hasn't been specifically designed to solve these problems, it's going to run into some real difficulty. There are fiddly jobs that robots just can't do very well. So, for example, even to this day, we don't really understand how heat from the interior of the moon diffuses out to the surface. And that's because the astronauts in the Apollo mission tried to drill holes and their technology wasn't very good and they had trouble drilling holes. And it's too fiddly a job for a robot. So we're going to have to send a person there to do it that way.
Why are we interested in heading back to the moon at all? Haven't we got bigger planetary fish to fry these days, like Mars?
Well, we absolutely do. But I think the first step towards frying those planetary fish is going to be going to the moon. In the coming century, we want to be exploring the whole solar system. We're going to Mars, and that's just the beginning, right? We want to be going beyond Mars and exploring all of our cosmic home. And I think human missions to the moon are a great proving ground for all the technology that we're going to need to help us along the way. It's very hard to test equipment in the environments on Mars, but the moon is basically next door in terms of space. So it's a really nice first step to our coming adventures.
Is it a jumping off point? Because some people have speculated, well, we put a base on the moon and then it's much easier to go places from there than have to keep getting off of Earth into space and then on to our next destination.
Yeah, that's exactly true. Earth is a big planet, right? We're sitting at the bottom of a very deep gravity well, and that's why you need such an enormous rocket to blast off into space. Gravity on the moon's surface is about 1/6 of the gravity on the Earth's surface, and so getting into space from the moon is much easier. So we're building these permanent installations like a moon base, and there's going to be an orbiting space station around the moon, a bit like the ISS. And getting into space from there rather than from Earth, I think, should be much easier in the future.
Do you know where they're going to build these bases? Will we be able to see them from Earth? Presumably they will want them on the side facing us so we can talk to people easily, because if they were around the other side, they wouldn't be able to talk to us so easily.
Yeah, that's exactly true. So any base with people in it is going to be on the near side of the moon so it can radio Earth. But there are reasons to go around to the far side of the moon as well. There are plans to build a radio telescope on the far side of the moon, which is going to be one of the quietest places in the solar system, because you can have thousands of miles of rock between your radio telescope and the noisy radio Earth. So in terms of exploring the distant universe, we might be going to the far side. So I think we're going to be exploring just more of the moon in the future in general.
So if you go out with one of your big telescopes doing your public astronomer bit, would you be able to see the settlement, or would it be just too small?
I think the settlements that they've planned will be too small to start with, but you never know what the future may hold, right? If there ends up being a permanent settlement of people on the moon, then in 50 years, 100 years, it really might start getting quite noticeable.
So watch out, you might have Matt staring at you, future moon inhabitants. Thank you, Matt. Well, Ella, let's come back down to Earth for a moment and come to you. Chris has been in touch and is interested in climate change, that sort of question, and climate modelling. What he says is it true that we could include measurements taken from centuries ago, or we do include measurements taken from centuries ago in our climate models? Are those measurements that our predecessors made actually reliable?
That's a really good question. Yeah, generally with climate modeling, we try to integrate as much kind of real world data as we possibly can to get the best kind of picture of what conditions are like when you press go on the model. And people have been collecting measurements of temperatures for a really long time. So it's one of the kind of first things that we can measure. But technology has improved quite a lot, thankfully, since the 1800s, 1900s, when measurements were taken using relatively cruder techniques. So, for example, using glass mercury thermometers, or one of my favorite stats is that before the 1940s, to measure sea surface temperature, people would throw a bucket overboard on ships, drag up a bucket of water and stick a thermometer in it. So you can imagine that on the process of getting from the sea up over the side of the ship, it would maybe change temperature a little bit. Whereas now we have different techniques. So we can use underwater buoys and robots to collect our data. We have automatic weather stations these days, which can record temperatures and things like this. So the ways that we collect those temperature measurements has changed. So stations where we record these temperatures, they might have moved, they might change the hour of the day when they collect the observations, and all of these things actually have an impact on the values that are recorded. So you can get essentially a step change when something changes in the way that the measurement is taken. So you have to adjust for all of these things, and there's some algorithms devised by cleverer statisticians than I that account for this. I think they call it a process of homogenization, where this accounts for the sort of step changes we see when a station moves or it changes the hour that it collects information at. The principle is that you can assume that climatic changes are broadly similar on a regional scale. So that if you're seeing in one station some really dramatic jump, you can assume that that's to do with the instrumentation changing rather than a very sudden change in the climate.
So Chris's point that our predecessors, scientists of yesteryear, may well have recorded things a bit less accurately than we would today, and possibly less precisely as well. But there may well be a bit of variation, but the trend is your friend, because if they did it consistently and they were a bit off consistently, it's the signal changing that matters, not so much the absolute number.
Exactly. And there's always going to be more uncertainty in yesteryear, because first of all, there were fewer measurements being made, and we know that the techniques were slightly less accurate.
From a historical point of view and your knowledge of Antarctica, are there bits of Antarctica that, say, Captain Scott would have walked on that no longer exist because of climate change? Would he recognise Antarctica if he went back?
In as much as one can recognise a vast continent that looks very similar, maybe. I mean, chunks of ice shelves, for example, have broken away. We get lots of year-to-year variation in the amount of sea ice that covers the ocean around Antarctica. In 1995 and 2002, we lost 2 entire ice shelves on the Antarctic Peninsula, which is a bit that sticks out. And lots of ice shelves regularly have gigantic chunks breaking away and turning into huge icebergs that circle the continent. But in terms of the stuff that's on land, I would say it probably looks relatively similar.
A vast expanse of white.
Yes.
Thanks, Ella. Well, thinking about, what is causing Antarctica to change, one cause is, of course, global warming, climate change. And based on what I was ribbing Matt a bit earlier about using his telescope to look at lunar bases and so on. But, I mean, this is a sort of serious point here. Gernot, we've been saying there's too much CO2 in the atmosphere. You're saying as a geoengineer, one possibility might be to inject things into the atmosphere that would reflect light back off into space and help to cool the planet like a volcano does. But could someone like you end up the arch enemy of someone like Matt because you'll fill the atmosphere with particles and that will mess up his ability to do stargazing?
Maybe we should probably take this outside, but
no, don't do that. We need to record this program.
Yes, but just to be clear, that might be one of the smallest possible impacts or risks of solar geoengineering. I mean, yes, right, it might change how the sky looks ever so imperceptibly.
Did you want to tell us actually what you would do then? Say you wanted to cool the planet, do it quick and do it safely. What would you put and where?
Yeah, so here's what volcanoes do. In 1991, Mount Pinatubo erupts in the Philippines. In 1992, global average temperatures are about 0.5 degree centigrade cooler than they would have been without that volcanic eruption. If you throw tiny reflective particles into the stratosphere, into the lower stratosphere, somewhere around the equator, those reflective particles within weeks spread around the Earth, and for a few months, for a year and a half, reflect sunlight back into space.
But what are those particles? Because obviously what volcanoes chuck out and do what you're saying they do, they're chucking out
a whole bunch of gunk. Right?
Exactly. It's sulfur,
yes.
For example. You could then get acid rain, couldn't you? Which obviously you're robbing Peter to pay Paul, because yes, you'll have a cooler planet, but then you'll have dissolved everything on the ground into the bargain. So how are we going to do this safely then?
It is sulfate aerosols. Often that's the sort of the most prominent example. Now, you don't get acid rain for the simple reason that up in the stratosphere, right, there are no clouds. So that, as many problems as there are with solar geoengineering, does not address that root cause. We should be doing the research, right? Nobody sensible is calling for actually deploying any of this now. We shouldn't. What we should be doing is figuring out whether it could work, whether the benefits, as far as they are, and there are great benefits here, lowering global average temperatures, whether they do outweigh the costs, the risks, the uncertainties.
Matt, I started this question by saying that, Gernot could get on the wrong side of you if he makes the atmosphere more opaque, so you can't see things so clearly. Have astronomers not got quite crafty ways of subtracting wonkiness in the atmosphere? So when light comes through the atmosphere, it causes stars to twinkle. The stars look like they're twinkling because light is bending anyway as it comes through the atmosphere. Have you not got clever adaptive ways of getting around this?
We absolutely do. So astronomers use the slightly stupid word seeing to refer to this kind of twinkly, bendy thing that light does when it comes through our atmosphere. And yes, we do have clever ways of dealing with it. So basically what we'd have to do is just make a model of the atmosphere, right? We live under 100 miles of turbulent, wet gas. And if we can understand what the turbulence is doing, then we can subtract that out and see clearly. A lot of the issue we have with things going into space is not so much about the bendy twistiness of light as it goes through the atmosphere, but just particular wavelengths being blocked or even overwhelmed. So the Starlink project, so Elon Musk's plan to put a bunch of satellites in space and broadcast internet around the world, that could be catastrophic for radio astronomy, because those things, it's like putting a bunch of mobile phones or internet routers in orbit. Any radio telescopes on Earth might just be absolutely bombarded by these signals from outer space. If it's for a good cause, it might be hard to say no. I mean, the night sky is very wonderful, obviously, and astronomy is important. But if it's a choice between that and fighting climate change, I think I know what side I'd be on.
We might need that telescope on the dark side of the moon that you were talking about earlier.
Exactly.
Much has changed for business owners, managers, and staff recently. But with over 30 years' experience in telecommunications, award-winning independent company Spitfire have the expertise to make sure you stay ahead and can keep on innovating. Whether it's connectivity, MPLS networks, firewalls, or phone systems, Spitfire can help. To find out more, go to spitfire.co.uk. That's spitfire.co.uk. Spitfire, telecoms and IP engineering solutions for business since 1988.
Music in the program is sponsored by Epidemic Sound, perfect music for audio and video productions.
Now, this episode is in fact a very important one. It's going out on what is the 20th anniversary since the Naked Scientists first took to the airwaves back in September 2001, when paleontologist Leslie Noe joined us armed with dinosaur claws, belemnites and ammonites that he'd been digging up locally. Now, here we are, 2 decades and about 120 million downloads later, and still going strong. Much of our success, of course, is thanks to you for listening and staying with the programme over all these years. But of course, it does cost a lot to run The Naked Scientists, so if you enjoy and appreciate what we do for you every week, please consider supporting us with either a one-off or a regular donation in recognition of our 2 decades on air. Would you send us £20 to mark our 20th birthday? We've made it very easy and secure if you'd like to do that. Details are at nakedscientist.com/donate. This week on The Naked Scientists, it is a Q&A show. We are answering your science questions that you've been sending in to us. And with me are a panel of experts who are answering them. They are climate scientist Ella Gilbert, climate economist and geoengineering enthusiast Gernot Wagner, ethnobiologist and plant explorer Cassandra Quave, and deep space astronomer, that's deep as in deep space rather than he's psychologically deep, Matt Bothwell. Now, time for another of the clues in our Guess Who competition this week. This is where we give you a sequence of clues to the identity of a mystery thing or object. I told you it sounds like this. Then I said this is a group of mammals that are indigenous to the Americas, Eurasia and Africa. And your third clue is their collective noun is a scurry. A scurry, not a slurry. That would be something different. A scurry. Cassandra, you've had 3 clues. Any ideas?
Oh, well, at first I thought it was a bird, but that's not a mammal. So I'm going to go with a rodent. Maybe some sort of rodent.
Cassandra's going for a rodent. Another clue coming up, which might put you closer to the identity of what this thing is. But I'd say that's a pretty good call. Now, as we always do on these programmes, we like to pause halfway and test the mettle of our panel with a quiz. And of course, you at home can try and see if you can have a bigger brain than they do, because you are competing, everybody, for a prize beyond price this week. It is the Naked Scientist Big Brain of the Week award that you're going to win. So they're going to be 2 teams. And team 1 is Ella and Matthew. Team 2, Cassandra and Gernot. Now, there are 3 rounds to this quiz, and conferring is actively encouraged because each team's going to get different questions. So do talk between yourselves and establish what you think the answer is. We won't be awarding marks for, unlike your maths paper at the exam, showing you're working, but we do like to hear it all the same. For you at home, this is your chance to see if you can outwit our panellists. Now, because the seasons are changing, and here in the Northern Hemisphere we are heading into autumn, we thought a good theme for the quiz would be change. So let's do round 1 first. Too hot to handle. This is a change in temperature. Question 1. Which of these elements will melt in your hand? A, gallium, B, bromine, or C, mercury?
So I think bromine is a gas at room temperature, so it's not going to be that.
Yeah, I wouldn't fancy handling any mercury.
Dredging this up from the depths of my memory, it might be gallium. I'm not sure. I'm more than 50% sure.
Well, that's more sure than I am.
Is that what you're going for?
Yeah, why not?
Yep, well done. It is gallium. Gallium is a soft metal. It's a silvery colour, as most metals are, and it will melt to a liquid at any temperature which is higher than 29.76 degrees C. Of course, your body temperature at 37 degrees C, give or take, means your hand temperature is capable of melting gallium. Bromine and mercury are already liquids at room temperature, so if you had them in your hand, unless they were starting off extremely cold, and that wouldn't be pleasant to hold, they wouldn't be naturally melting in your hand. Right, 1 so far to Matt and Ella. Team 2, Gernot and Cassandra. Here's your question. Verkhoyansk in Russia is the place on Earth with the greatest range between its highest and lowest recorded temperatures. Is it A, 66 degrees C, B, 86 degrees C, or C, 106 degrees C? What do you think?
Okay, so 100 is a bit high, right? We are talking minus 40 to plus 60. That doesn't quite sound right. So how about the middle one here?
Yeah, I concur. We'll go with that. We'll go with the middle.
You're going 86 degrees. I'm afraid. No, the answer is actually 106. Verkhoyansk is home to over 1,000 people. It holds the record for being both the hottest and coldest place at different times. And it has the widest temperature range, therefore. It's recorded a scorching 38 degrees C on some occasions and a brisk, shivery -68 on others. So
I was sitting on my hands the whole way there because I knew
106
that.
degrees. Oh, there you go. Now you know why we didn't make you team 2.
That seems hot.
I'm thinking of their closets.
By about
What kind
1,000.
of clothes? I mean, how do you prepare for a year like that?
2 wardrobes.
You need 2 wardrobes.
Two
Quite
wardrobes.
right, Ella.
Yeah.
Right, Ella and Matt, back to you. Your question. The salmon are famous for swimming upstream from the ocean along rivers in the autumn to reach their spawning beds. This is a race called the Salmon Run. But what's the average speed that sockeye salmon doing that migration do on the Fraser River? Is it 0.9 kilometres an hour? Is it 2.4 kilometres an hour? Or a speedy 6.8 kilometres per hour? What do you think?
It feels like a Monty Python question to me.
It really does. Depends how fast the river is. I feel like maybe the middle one.
Yeah, like based on nothing but intuition, just throw the dart at the map.
6
And the
kilometers
middle
an
one,
hour is fast.
Yeah, like that is pretty fast, right?
Well,
But
a
then
fast
they're-
shark or a tuna will do 60 or 70 kilometres an hour.
Yeah, but this is an average, right? Are they going like uphill, up rapids? That's what you always see in the nature docs, isn't it?
Yeah, that's
Bears
faster than
leaping
walking
at 'em.
pace. Faster than walking pace seems fast for an average.
Matt's going for a more sedate 2.5 kilometres an hour. Is that your answer?
Yeah, I'm imagining a pretty chilled out salmon going down the river, you know?
The public astronomer says 2.5 kilometres an hour seems like a sedate speed for a salmon. Seems good. And you're absolutely right. Yeah, it is actually 66.75 centimetres per second. It's been demonstrated that the most efficient speed to travel at, if you are a sockeye salmon, is 1.8 kilometres an hour. But that wouldn't work if you were going to miss the festivities and not get to your spawning beds in time. So that's why they swim a slightly less sedate 2.5 kilometres per hour. Cassandra and Gernot, back to you. Your question is, Mars has a longer orbit around the Sun than we do here on Earth. And Matt, you'll know why you didn't get this question. It means that the seasons are longer on Mars. To the nearest whole number, how much longer are the seasons on Mars? Are they A, twice as long, B, 3 times as long, or C, 4 times as long as they are on Earth?
I don't know. I wonder how far is Mars from Earth? Maybe that could help. I know it's really far.
Mars is tilted by about almost the same tilt as Earth, so it has seasons for just the same reason.
It's great. Can we phone a friend? I want to have Matt for just a moment.
Matt's not going to
So
help
wait,
you
one of
here,
the
I'm
options
afraid.
was twice as long, right?
You've got twice as long, 3 times as long, or 4 times as long. What do you think? Gonna have
Twice
to
as
push you
long.
now. You're going twice. Do you agree, Cassandra? You're going twice?
Let's go with twice. We'll go with twice.
One Martian year is 687 days, and that's almost twice as long as an Earth year, so the seasons are roughly twice as long. As Matt says, that Mars is tilted in the same way with roughly the same inclination that the Earth is, which is why it has seasons, and therefore they're roughly in proportion to the Earth's seasons as well. So it is.
So is that why Elon wants to go there, just to have every year be twice as long?
The thing is, you come home and you're only aged by half as long.
Exactly.
If you
yeah,
believe
fair
that, you'll
enough,
believe
yeah.
anything. Right, round
This is
3.
a fountain.
This round is called A Change in Time. It goes by so slowly. Question 2, Ella and Matt. Getting a handle on different time zones is important in the time of online communication. But over the last couple of years, no one has really made any drastic changes of them for the sake of Zoom calls, for instance. But that wasn't the case in 2011, when which island decided to jump ship and skip a day out of their calendar, which the victim was the 30th of December, to jump across the international date line and become one of the first countries to see in the new day of that year, and the subsequent new year, of course, rather than one of the last. Was it Samoa, Fiji, or Tonga?
I remember this happening, and I can't remember which one it is.
Yeah, same. I watched a YouTube about this quite recently because they wanted to be able to do business with Australia, right? Because I think the problem was it was Friday for the island and it was Saturday for in Australia, so they
I
couldn't
can see
do
why that would be a
business with them.
problem. I don't think it's Fiji, but I'm not basing that on anything.
Yeah, no, let's go with your gut feeling.
And it's a good call. It is Samoa. Well done.
Yes.
Yep. The date line runs across the Pacific Ocean. It separates one day, literally, from another. And American Samoa is on the eastern side of the date line. And that means that those two regions are separated by a whole day, even though they're only 30 miles apart. Well, that puts you in a very much unassailable position. I'm pleased to say for you, Matt and Ella, it does mean that for Cassandra and Gernot, it is a winning streak not for you this week. But I'll give you the last question anyway, because this is your opportunity to partially redeem yourself. I hope you know about koalas. When a koala's born, it's about the size of a jelly bean. It's got no hair, no ears, and it can't see. But how long is a koala's gestation period? In other words, how long is it pregnant for? 7 to 14 days, 28 to 35 days, or 63 to 70 days? What do you think?
Okay, let's think about this. I think they're so tiny, right? When they kind of mature outside of.
Yeah, shorter, I believe, but frankly,
Yeah.
my wife's a human gynecologist, so I wouldn't be able to. What was the middle one? It always sounds right to be in the middle.
7 to 14 days, 28 to 35 days, or 63 to 70 days.
I mean, to go from a cell to like something that would be large enough, I would say like a minimum would be 28 days, I think, right? Like to get to a decent enough size to survive outside.
So we're going with 28 to 35 for the pride?
Yeah, I think so.
And it's a good call to make because it's the right answer. Yes, it is 28 to 35 days. Very well done. Unfortunately, you are not the Naked Scientist Big Brain of the Week award winners this week because that accolade goes to Ella and to Matt. So let's give them a round of applause. Well done, guys. Excellent demonstration of knowledge of time and change. We better get back to the questions. Let's kick off with you, Cassandra. We constantly hear about, especially my job as a microbiologist, of the dangers of antimicrobial resistant superbugs. Can your field in plant ethnobotany and medicine, natural remedies, do anything to help us in this area?
Absolutely. I mean, we have a couple of problems that's really spurring antibiotic resistance. One of them is, misuse of our existing antibiotics, not only with regards to overuse in the clinic, but also massive use in agriculture. So we need to work on that. We need to work on also the economic models for developing antibiotics. But the main problem that we're focused on is really helping to fill that pipeline. We need new molecules, but we also need new approaches to dealing with infection. And this is where traditional medicine, I think, can really provide some important clues, because even in our own work, we found that healers don't always treat an infection with plant products that kill bacteria. A good example of this is our work on pepper tree and on chestnut. These are used to treat wounds, but they don't have growth inhibitory effects against the bacteria. Instead, they shut down the ability of bacteria to cause harm. So I think from my perspective, yes, plants have a lot to offer in terms of novel chemistries, and they may actually open the doors to new ways of dealing with these infections.
That's very interesting. So rather than just kill them outright, you just basically render them a bit impotent. So the bacteria are much less able to cause disease, giving the body a helping hand.
Exactly. I like to liken it to, taking the teeth out of the dog's bite, right? The dog's still there. He may gnaw on your arm, but he's not going to do much damage without the
just
teeth.
Licks you to death, which my dog seems to do. Fantastic. Thank you. Thanks very much, Cassandra. Now, with me this week, I have got Ella Gilbert, Gernot Wagner, Cassandra Quave, and Matt Bothwell, and we're tackling the questions that you have been sending in. Time for your fourth and final clue in our Guess Who competition this week. This is where we give you a sequence of clues as to the identity of a mystery thing or animal or object, and you have to try and work out what it is. Can you beat our panel? I said it sounds like this. This group of mammals, which they are, is indigenous to the Americas, Eurasia and Africa, and the collective noun for this group of mammals is a scurry. Now, your fourth and final clue is these mammals are famous for their fluffy tails, so much so that their English name derives from the Greek for shadow-tailed. Now, Matt, your opportunity to shine here and demonstrate your knowledge of Greek. So,
I didn't know it until this last one. Is it squirrels?
Matt speculating a squirrel. You'll have to wait and see. Now, Matt, since your head is above the parapet fairly and squarely, in 1181 AD, the guest star appeared for 185 days and then it slowly disappeared and diminished in brightness. Earlier this year, researchers were able to classify that object retrospectively as a supernova. How, Peter's wondering, can we go back and identify astronomical events like those and work out what they were?
So fundamentally, what we have to do is just look at the patch of sky, which isn't always easy, right? Because these ancient peoples 1,000 years ago didn't always have very accurate ways of telling where things were in the sky. So we have to kind of take their descriptions, look at the patch of sky, and just try and piece things together by looking for whatever might have been left behind. The 1181 guest star has historically been kind of tricky. It was probably some kind of supernova. When something appears in the night sky and then lasts for a few weeks or something, then fades away, some kind of supernova is normally a good guess. This one was a bit weird though, because it took months to fade away, which is much, much longer than normal. There was only one thing in that patch of sky that we used to know about that could have come from a supernova. It was a pulsar, the compressed core of a dead star called 3C85. The problem is, when we aged it, it came to about 7,000 years old. So not a good candidate. It was a much, much older supernova. This new result, which got everyone really exciting and has solved this 900-year-old mystery, is that we found the smoking gun. We found this new supernova remnant, and we combined it with a distance measurement taken from this satellite called Gaia, and we've worked out that it's about 1,000 years old, which makes it perfect, right? It's a supernova remnant. It went off around 1,000 years ago. And now we know these things, we can go even further and investigate it. So people at the time noticed that this thing was about the same brightness as Saturn, which is a pretty good yardstick. So now we know how bright it looked and how far it is away. We can work out how intrinsically powerful this thing was. And it turns out it was actually pretty wimpy as supernova go, which is kind of interesting. It was a wimpy little explosion, but it also took 6 months or something to fade away. That's a clue that it was actually something very, very rare. So our best guess now is that it was two white dwarfs crashing together, and they've left behind something called a Wolf-Rayet star, which is a very, very hot star full of all kinds of interesting heavy elements. So yeah, it's going to need a lot more investigation, because this was a very, very rare event which has left behind something very exciting.
This is like stellar or cosmic archaeology almost, isn't it?
It literally is, yeah. So all astronomy in some ways is the study of the past, because the signals that we're seeing from the universe have taken thousands or even millions of years to reach us. But this is taking that to another level. And because we literally are doing archaeology, we're looking in the sky and then we're trying to put the pieces together and work out what happened 1,000 years ago.
Thanks for that. What a fascinating story. Over to you, Gernot, because Michael wants to know, why is green energy typically more expensive for the consumer? Indeed, is it? Is that true?
So traditionally it has been, right? Which is why we have this climate problem in the first place. Burning fossil fuels was cheap, available, largely because nobody paid for the pollution. Nobody paid for the fact that we are dumping gazillions of tons of CO2 into the atmosphere. We should pay for that. But even without paying for it, by now, solar PV is the cheapest form of electricity in history. Costs have come down so quickly. 40 years ago, it was about 100 times as expensive as today. 10 years ago, it was about 10 times as expensive as it is today. And yes, by now, in sunny locations, of course, right? Don't put your solar panel on the north side of the roof if you're in the northern hemisphere, sure. But assuming it's sunny, solar PV is cheaper than any other way of generating electricity. And to be clear, that's a big deal. And that information comes from the International Energy Association, which is nobody's idea of an environmental group.
The install costs are very high, aren't they? I was looking at this yesterday, and the payback period for a domestic system might be 25 years in some cases, especially in a less sunny place like the UK.
So, of course, you are sitting in the UK, which, I'm sad to say is not one of the sunniest places. And no, that's okay. But sometimes there's an advantage of being, in southern latitudes. So even here in New York, right, which isn't all that far south, to be clear, the payback period is a lot shorter. And yes, right, of course, it depends on, having a sunny location. But the key thing here is, yes, there's upfront cost. But then as soon as you have the panel, you're basically, printing money for free. You're printing electricity, right? There's no further cost other than, wiping down the panel every once in a while. So that's the big difference here, right? You're not paying for the fuel through.
But can I pick you up on that, Gernot? Because a few years back in your wonderful country, there was this initiative to produce biofuels because everyone said we need to make sure that we don't emit more new carbon into the atmosphere. So we'll make fuel from the atmosphere. We'll grow plants. The problem is that lots of good agricultural land was then used to grow plants, with the result that then you had to ship in food from places with a higher carbon footprint than had you just grown the things at home. We're also in danger of turning over quite a lot of agricultural land, especially in some countries, which is at a premium, to turn it into a solar farm. So on the one hand, you're incentivizing people to produce cheap green electricity, but then the carbon cost of shipping in your food because you're not growing it on that land from elsewhere could be much higher. So one has to be very careful about these sorts of carbon equations.
Absolutely, right? And in some sense, that's the bread and butter of what economists do, right? Figuring out those trade-offs. You can go back to philosopher Mick Jagger on this one. You can't always get what you want. So yes, there are trade-offs, clear. And yes, right, so don't get me started on subsidies for biofuels in the US, right? Why do we do that? Because the presidential primary starts in Iowa and there's a lot of corn in Iowa, and that's why we'll never get rid of those often misguided subsidies. There's lots of politics here, of course. That said, yes, there's plenty of marginal lands where we are not growing food, where very little else happens, and yes, where a solar farm would make sense.
Well said. Let's come to bits of land that might have interesting plants on them, and the question back to you, Cassandra, of delving into nature as a medicine chest. I'm intrigued by your role as someone who runs a herbarium, because there was a great story a few years back where scientists actually worked out from stored specimens what caused the Irish potato famine. And that was done in the southeast of the UK. They happened to have a specimen, and they could work out what caused something that happened historically over 150 years ago. Are you able to delve into what you've got in herbaria to find treatments? Or are you having to actually get out there in the wild and look at the real deal?
That's a great question. Well, first, let me just explain what an herbarium is, because I think sometimes people envision this lush tropical greenhouse. And in fact, an herbarium is a museum of dead plants that are pressed to paper. So I always tell my friends I have a brown thumb. I'm very good at finding and killing plants and drying them and gluing them to paper. But herbaria are incredibly important as records of life at specific points in time in specific places. So your mention of the Irish potato famine, those specimens, are a record of what the crops looked like, what other microbes may have been on the leaves at that time. And also, we have now, with more advanced chemistry tools, we can look into the chemistry of fragments of those specimens. But in reality, when it comes to drug discovery, of looking for new molecules, we generally need a lot more material than what you would find just on a pressed specimen. So we're talking about 40 grams of dried leaves to really kickstart the search process. But those herbarium specimens are incredibly important for authenticating and really having a documented record of which plants you're working on. This is a big issue in the literature because there are lots of publications on plants, including clinical studies on botanical remedies. And some of the reasons we get into trouble with seeing different outcomes is often these studies don't really have rigorous authentication of their materials, and the chemistry, even of related species, can be quite different. The chemistry of the same species can be different also depending on where it's grown because of the influence of environmental factors. So really controlling for records of what species you're working on and also controlling for or characterizing the chemistry is really important to that process.
Going back to something we were talking about earlier with climate change causing loss of plant species, we've also got the technological revolution causing loss of some cultural values, haven't we? People are increasingly moving to cities and they're abandoning their relationship with nature. Is there anyone out there, or are there projects out there to try and capture that vast local knowledge before it is lost to the technological revolution, so that we've got those sort of folklore remedies stored somewhere so that people like you can subsequently follow them up and hopefully find the next blockbuster drug in the future?
I mean, absolutely. That's really the bread and butter of what ethnobotanists do in the field, is recording traditional knowledge, and sometimes we also call it traditional ecological knowledge, to really document the ways that people use plants in different cultures. We've done a lot of work in the Balkans and had a really nice study a number of years ago where we looked at two different cultures that had two different languages spoken, different practices. And we really examined how those cultural lenses influence the way that they interacted and engaged with plants in the same environment. So they're in the same mountain range, relatively close to one another, but don't intermarry. And there were huge differences in how, not only how they named plants in these different languages, but also which plants were used for food and medicine. Even in places where you had the same species growing, the historical trajectory, that cultural lens is incredibly important. And we're in a race to save that knowledge before it's lost forever.
Sobering. Thank you, Cassandra. Matt, some of the things in the universe can't be seen with the naked eye. You've written a book about some of them recently. Why do we need to look at something that we can't see?
Well, the quick answer is that there is an awful lot more that we can't see than we can. I'll give you an analogy. So the difference in wavelength between the reddest and bluest light we can see is roughly a factor of 2, right? So the bluest light we can see is around 380 nanometers, and then the reddest light we can see is about 740 nanometers or so. And so we have this like factor of 2 in wavelength, which is our window that we use to see the world. There's a nice coincidence. A factor of 2 in wavelength also has meaning in terms of sound, right? So a factor of 2 in wavelength is 1 octave. So if you think of red light as being middle C, then the bluest light we can see is the C 1 octave higher, right? And then that octave is the window that we use to see the world. The full spectrum of light that arrives from the universe is about 65 octaves. That's 9 grand pianos standing in a line, right? If you imagine all those pianos being played at once and you could only hear one central octave, you would miss almost all of the music. And that's the problem with astronomy. If you're only looking with our eyes, you're missing almost all of the information that's out there.
And what's the solution?
Well, the solution is to build instruments that can see in different wavelengths. I'll give you an example from my research. There's a species of galaxy in the early universe that is completely invisible. If you look using the light we can see with our eyes, what we call optical light. And these galaxies are amazing. They're some of the most powerful factories for stars in the whole of the universe, but they're all cocooned away behind shrouds of dust. Just no light leaks out. But we go to long wavelengths like infrared and radio waves, and we can see through the dust and discover these amazing galaxies. You know, if you were a biologist and you could just strap on a pair of infrared goggles and see brand new invisible species, that would be the discovery of a lifetime. And that's kind of what we can do with astronomy. We can go to these other wavelengths and see things in the universe that we just didn't know existed.
And is this big business now? Is this really the next step forward then? People are beginning to explore new wavelengths, new regimes to see through these dusty shrouds that we couldn't penetrate previously.
It is absolutely big business, yes. All of modern astronomy is this multi-wavelength affair. The job of modern astronomers is to collect all of the data from across the spectrum and combine it all into one big synthesized picture of what the universe is doing. And there's even stuff beyond that. So modern cosmology tells us that most of the universe is invisible full stop. So it's made of dark matter and dark energy that we can't see at any wavelengths.
Is it not also true that you know, a sizable chunk of the universe is off limits to us anyway, because it's growing and growing away from us faster than we could ever let even light catch up? Even if we could travel at the speed of light, we could never get there and enjoy the restaurant at the end of the universe, because it would have invented more universe by the time we got there.
Yeah, that's exactly true. There's this thing called the cosmic horizon, which is a bit like the horizon on Earth. It's the bit that you can't see. It's a very long way away. It's about 46.5 billion light years to the edge. But beyond that, we just don't know, right? The universe might be infinite, or it might have an edge. We might never know because we are trapped inside our cosmic horizon.
We like to tackle the simple questions here on The Naked Scientists. Well, look, something a bit more trivial to finish on. You speculated, Matt, that this could be a squirrel, our Guess Who quiz this week. I'm pleased to tell you, actually, the nest of this animal, I was going to say as a final clue, is a dray, which is, of course, a squirrel's nest. So you were spot on. You won the quiz this week, and you even got the Guess Who. Did you at home beat Matt to identify the mystery thing as a squirrel? If so, very well done. That brings us to the end of the programme. We have to leave it there, but thank you to our wonderful panel, who were Ella Gilbert, Gernot Wagner, Cassandra Quave, and Matt Bothwell. And next time, with echoes of empty supermarket shelves causing concern in the UK, we are looking at some of the other things that we're at risk of running out of. From sand, believe it or not, to tequila, we're exploring the surprising and important resources that are endangered. The Naked Scientist comes to you from the Institute of Continuing Education at the University of Cambridge. It's supported by Rolls-Royce. I'm Chris Smith, and from us here at the Naked Scientist team, thanks for listening and goodbye.